Oh, thanks. Thanks, Andy. Great. First, I'd like to thank Andy, the Bay Area Spark Meetup Group, and Alicia for helping put this event together. Thank you, guys. Really appreciate it. So as Andy said, I'm Tony Chong. I am the DevOps and Data Engineering Manager. I've been doing this for some time, over a decade. What's that? Oh, sorry. Well, that's enough about me. Let's get into it. So here's our agenda. I'm going to give you a brief introduction as to kind of what we were doing for the last couple years. Ben is going to come up, speak about the old architecture, kind of what we're doing today. Then we'll pass off to Sasan, who will talk about how we're decoupling services on our ad serving platform. And Ben will then follow up with talking about our streaming ETL processes, and then we'll conclude with a Q&A session. So this was our ETL for, I believe, the last 2 or 3 years, right? We had one monolithic Java process, right, that crunched data, right? So what that means for us is that we had a variety of different data stores, and this Java process would basically suck that data in, do some crunching, and then pass that down to our downstream data stores and third-party analytics engine. Like most legacy processes, this ran on cron every hour. Right. In the last 6 months, Vungle has seen tremendous growth, exponential growth. And as you know, when you get more traffic, you get more data, things start taking longer to process, our cron job started running into some problems, right? We ran into jobs that are running over each other. Our heap size went from 12 gigs to 24 gigs. For those of you that are in ops, cron is like not even a management, it's just job management system. It's just like, it's a poor man's scheduler. And every time something fails, we have to like triage and then run everything like from the beginning, which is kind of a pain. So before it got out of hand, we started thinking about 2.0, right? What is 2.0 ETL at Vungle? We had some requirements. First, it had to be horizontally scalable. We're looking for real-time ETL processes, and the data had to be set up in a way that was reusable by the different engineering teams at Vungle. In summary, we basically had a lot of data coming from different data sources. We had a monolithic process, and we decided to use Spark and Cassandra because it seemed to meet our use cases perfectly. So with that said, I'd like to introduce Ben Ryder, who will discuss kind of what we're doing and how we're taking care of business.
Thanks, Tony. Thanks, Tony. My name is Ben Ryder. I'm a data engineer here at Vungle. So I want to tell you a little bit about our ETL process. We do around 1 billion events per day here, peaking at around 700 to 8,000 events per minute at any moment during the day. Our ETL process, one of the main issues we have to deal with is deduplication, from SDKs that have unreliable networks to reading off of Kafka, which doesn't guarantee exactly once, to anything in between. We face a lot of possibilities of seeing an event multiple times. Any ETL system we build must be able to handle deduplication on a massive scale and not get concerned with seeing multiple events and counting them many times, or else we could really run into trouble. It is also the process by which we calculate money. It's how we calculate advertiser spend and publisher revenue. It's how we make sure that we're paying out the right amount of money to all the people who make these games and are playing our ads for them. So it's really important that we get that right. And it's also the system that powers our dashboard, our reporting API, and all the different third-party tools that people use to look at our data in different ways. So let's take a look at what the old architecture looked like. So it all starts with the SDK. It requests an ad from the ad server, it gets a response, it plays an ad, it tells the ad server how the ad went, and then maybe an install happens later and tells us about that too. So when it gets an ad request, it talks to some cache databases and talks to data science in order to make sure it's showing the best ad to the user. But it's also connecting to a Mongo database. And it's writing every single view and install that's being told about directly to that database. So when you have 1 ad server or 10 ad servers or even 50 ad servers, you can do okay. But we have upwards of 300 ad servers, each running 8 different node processes, each having their own connection pool to that same Mongo database. You can see how that could quickly get out of hand. Additionally, once it's all in that database, that one legacy Java process that Tony was talking about pulls all the data out, crunches it all in this one vertically scalable Amazon instance, and then outputs to dashboard and other sources that we care about. So that's kind of the old process, and it doesn't make me feel very good because as we added a lot more servers, as we added more things, we were having problems with different parts of the system, and turbulence in one part could kind of bring down the whole system. So we wanted to kind of separate it out and make sure that as each part needed more resources, we could give it as needed. So let's look at what the new architecture we built looks like. So it still starts with the SDK and goes to the ad server. But now, instead of being directly connected to a database, it actually has Flume running on it. Flume, for those of you who don't know, is a log shipper. It's a log Flume. That's the idea. And so we'll write the logs directly to a file, so all requests get moved to a file. As Netflix said last week, last Spark Meetup, Netflix is a logging company that plays video. Vungle is a logging company that also plays video. So the logs all make it to Kafka, and then from there they get picked up by Spark, which has the wonderful Kafka connector, and from there it gets pushed out. Essentially, Spark and Cassandra with Kafka have replaced our ETL system. And as I'm sure many of you know, as Kafka needs more resources, we can just add more machines. As Spark needs more resources, we can just add more machines. And because our ad servers are now only communicating with cache databases in real time, we can also add more ad servers as we need. So this kind of gave us a lot of security and a lot of protection as we continue to grow and scale. So to talk about how we started doing that process, I'm going to bring up Sasan to talk about the decoupling process that got us started.
All right, thanks, Ben. So my name is Sasan. I work with the ad serving team here at Vungle. And today I'm going to show you guys how we moved from our pretty coupled design to a decoupled design where we could scale. As Ben showed you guys, this used to be how we connected to our databases. So this has a couple of issues. The biggest one being that the ad server is doing a lot of things. It's responding to request ads. It's doing data aggregation, and it's doing a lot of reporting. Plus, this doesn't scale. Why not? Because as we add more service to this, we are maximizing the number of connections to our database. So what is the solution here? The solution was to add to let the ad servers do one thing and one thing only, and that is to serve ads. They will log every event that comes in, and then pass that to Kafka. Kafka will stream that out, and anyone that needs to use that data to do anything, any sort of data aggregation or anything that has to do with the data, with the event, will take care of that. So again, as Ben showed you guys, the SDK sends a request, the ad server logs that into Flume, Flume picks that up, sends it to Kafka, and that will get streamed to Spark. To solve our issues with the Mongo connection, what we did is that we wrote a really, really simple Spark job. And the purpose of that was to grab all the logs, aggregate the data, and put it back into Mongo. So to give you guys an idea, this is the final design where the ad server loads to Flume, picks up by Spark jobs, and it goes to Mongo database. Here's the Scala job that we wrote for Spark, which is, as you can see, is very simple. We connect to Mongo, we set up our streaming context, and then write to Mongo. So the first part of this program is to, set up checkpoints, get a streaming context, and set up a pool, connection pool. The second part is to map that stream, the Kafka stream, into into a Mongo object and then put it back into Mongo. So this solved a couple of issues. Ad server is doing one thing and one thing only, serving ads. Plus, we're not exhausting the number of connections to our Mongo database. Why not? Because we're creating a single connection pool on the driver, on the Spark driver, and passing and letting each worker to take care of creating a connection or grabbing a connection and putting it back in the pool. This allows us to scale horizontally. As we add more servers, we don't have to worry about the number of connections to Mongo or if the server is doing too much work. So that's pretty much it. We have a decoupled system, and we can build on that with the streaming of our ETL. So I'd like to open it to any questions you guys have right now with respect to our decoupling. If not, I'm going to pass it to Ben to tell you guys about the ETL process.
Thanks. So that was kind of our first step towards being able to decouple our ad servers. And then after we kind of got that up and running, we're moving towards this more streaming process. So that was obviously still using the same Java process that we were using before. This just enabled us to move out of having a limited number of ad servers. So I'm going to talk now about the streaming system that we created to kind of move us further in that direction. So we're going to be focusing on just the Spark and Cassandra aspect of this. So let's look at what that little section looks like blown up. So this is kind of a lot to take in, and we're going to look at this piece by piece. But what I want to call out is that this first part is what I'll refer to as the ingestion process. This is the Spark streaming job that connects with Kafka, pulls events into Cassandra, dedupes there, and then moves it to a fact table. So before I get too far into that, I want to describe two tables that we're using, an ingestion table and the fact table. So the schema of the ingestion table is pretty basic. We have an event ID that's shared by all of the events that we have, and a whole bunch of dimensions, and then some Booleans that will generally either be null or true as opposed to false or true because we're upserting it to Cassandra. So we have requests, we have reports, we have installs, and then we have request added, report added, and install added. The idea is that when the event comes in, you'll set the request, and then after you've processed it, you'll add the added flag to it. So on our fact table, however, it gets a little interesting. Instead of having a simple primary key, we actually have a massive primary key. All those dimensions that we were storing that came in on a request, where the ad was playing, what language the user's device was in, what device model they're on in the first place, all of those things become dimensions. Then, I think your battery's dying. Yeah, I think the battery's dying. Let's see. This one works. OK. So all those dimensions become the primary key. But importantly, the date time is used as the clustering key. So it's still part of the primary key, but it's not part of the partition key. So what ends up happening is that Cassandra will kind of uniformly divide all of our data across all the partitions, but have it still queryable and filterable by date. So let's break down this ingestion job a little bit. First, we read off the three topics, report add, request add, and installs. And we add them into the ingestion table, setting the appropriate flag to true. If it's a request, request. If it's an install, install. Each of these data types only affects certain columns. So even if we get a shared event ID at the same time in two different topics, they won't stomp on each other's writes. They'll both write to different columns, and they essentially won't care that they're both writing at the same time. Can
you say more about what each of these three types of things is?
Sure. Yeah, so as I was saying at the beginning with... Can you repeat the question? Sure. So the question was, can I repeat what each of those three topics are semantically? So when the SDK first asks for an ad, you can imagine you open up a game and it's getting ready to play an ad at some point. It sends a request. We call that internally a request ad. So it sends a request saying, hi, I would like to play an ad. I'm from this device. I'm in this app. The ad server will then generate a unique event ID and send back down information about the ad we want it to show. It will then play that ad, and after it's done, it will phone home and say, hi, I played an ad. The user clicked on me, and they also clicked out of me after some amount of time. And then at some later date, a partner such as MAT, which is mobile app attribution, mobile app tracking, or Kochava, which are companies that work in the mobile app space to figure out which advertising partner actually gets credited with an install will send us an event saying, this device have added this app, and it was associated with this event ID. So essentially, installs can come from either the SDK itself, which is when the app opens, or from a partner who's telling us that this app was just installed. Report ads are from us, and request ads are at the very beginning of the chain. Part of this process is tying everything back to the request that originated it in the first place, instead of allowing views to be trusted as they come in. Does that kind of answer the question? Cool. All right, so we've gotten this stuff into the ingestion table, but we've left a lot of stuff null. So let's figure out what's happening next. So we query the table once for all three of the topics. Instead of doing it like once for each topic, we just do one big query. We filter out. So we find the requests that we've seen but haven't added yet, the views that we've seen but hadn't added yet, and the installs that there is a request for but we haven't done anything with yet. We then figure out like what they are. If it's a request, it increments delivery. If it's an install, it increments installs on the fact table. We calculate the dimensions to produce a primary key, and we increment counters on the fact table, and and then we go back to the original ingestion table and set the request added flag or the view added flag to be true. When we're requesting with local one consistency, but when we're writing with a local quorum. So we're hoping that this will guarantee you that we do not see the same event twice in the process. Something I should have mentioned back on this slide about the fact table schema is that it has essentially 6 counters on it: deliveries, views, installs, and then unbeknownst to the ingestion process, it also has process deliveries, processed views, and process counters, and process installs. What happens is that in this process, we're incrementing the views, clicks, and installs. The views, installs, and requests. But then when we pull out of the fact table, we're going to be looking at the other half of these two. So in the process, the second half of this system, we're going to query the fact table, calculate a delta. So requests minus process requests, views minus processed views. In other words, how many views have happened since the last time this process ran? Then we take that difference, we find the various view tables that we care about. We extract the campaign ID from the primary key, the creative ID, the publisher ID. We go to the view tables and we increment the appropriate fields there. We go back to our fact table and we set the processed fields equal to what we just incremented on the other side. So even if more requests, more events, more installs are happening in the ingestion side, this system doesn't care about that. We'll take whatever it was at the time and be able to pick up the events that occurred later the next time it runs. So this should be able to ensure that we don't have any duplicated events, we don't count anything twice. So that's the process. Next steps for us are we're currently using JSON as our serialization method, so everything logs JSON. We've had some problems with that, especially with a large and distributed team. As people change formats, not everybody is always informed. So we're switching to using protocol buffers, and we think that's going to make a big difference for us. We're also planning to start using Yarn for our resource manager. We're currently using the standalone manager, but we think that we might be able to get some better performance if we can run multiple Spark jobs on the same cluster and really fine-tune the amount of resources that each one gets. Also, our data science team is making extensive use of Spark. They're not quite ready to go live with anything yet, but they've been finding it a very helpful tool for both building models and potentially using the streaming function for actual live data processing. And we really don't know what else. We think we're going to do a lot of stuff with it. I taught one of our product guys this past week how to write a simple Spark job to do some analysis. We're finding it to be a very generally useful tool for doing large-scale data processing without too much work having to go into it in the first place. So that's it. I would like to call back up Tony and Sasan to answer any questions that people might have.
Yeah. So
the question was, as far as deduplication goes, are we using Spark for the querying, or are we letting Cassandra do it?
yeah.
So,
I have a follow-up on that too.
sure, OK. So we're using the Spark Cassandra connector that's built by DataStax.
Yeah.
And so for most of the filtering, we're doing it in Spark. We can't get Cassandra to do it because we can't get the indexes right, basically.
Okay. So when it comes to deduping missing things,
Yeah, so the question is, I think I can sum up as basically saying, how do you handle consistency issues when you're writing to a Spark when you're writing with Spark in a cluster? So we think that we're handling it by always writing with a local quorum, and then always writing with a local quorum and then reading with local one. So with local one, we're pretty confident that we'd have consistency issues, obviously. But we're always writing with a local quorum, and then we're querying sometime later. And because we're always writing to the same primary key but different columns, we're not that concerned about kind of stomping on our own writes. The biggest concern would be we write and then we query a little later, and the quorum hasn't actually reached every server in our system. We haven't observed that, but that would be a big concern for us. Does that kind of answer the question?
Yeah, well,
So that's on the fact table, but the main table that we're doing deduplication on is on the ingestion table.
yeah, okay.
So the ingestion table is keyed on the event ID.
Okay.
It's probable that we would see that same request, that same report multiple times,
Yeah, yeah.
but we're saving only the values and not touching the value about the view added. So you can imagine we see it, we process it, we tick the added flag to true, we see it again, it comes in, we query, and then we filter it out because it's never modified that column again.
Okay, got it, thanks.
Cool.
So you have.
Sure. Tony, would you like to talk about that? Yeah. So the question was, I see that you're using Kafka and Flume. Can you talk a little bit about the latency you're seeing between those two services?
Sure. So we haven't seen any latency. So the way basically, technically how it works is it's two processes. It's really Flume and log rotate. So what we do is every minute we rotate a log and it dumps it into a directory, and then Flume picks it up. And we're processing, wow, like billions of records a day, right? And I mean, at that point, we haven't seen any real problems. So it's pretty stable. Does that answer your question?
So my question was like, so there's a 1 minute delay.
Yeah. So the question is, is there a 1 minute? Yeah, there is a 1 minute delay because Flume doesn't, at least as far as I know, doesn't like support like a tail function, right? So we have to find some way to dump that into a place that Flume knows about, and then so it's on a 1 minute rotation. Does that answer your question?
I think it does support a tail, but we tried it out early on and found that it wasn't able to keep up and that we were concerned with the buffer, and that we found much better performance from the file swap.
Can you talk a little bit about the infrastructure, like the servers to manage, like nodes?
Sure. So the question was, can you talk a little about the amount of servers you're using, the infrastructure you're using to make this all work? Talk about Kafka.
Sure. So starting from the very front of the chain, which is the ad server, we have 350 ad servers in production. Right now, we're looking at 30 Kafka servers. I believe we're using D2 XLRs. Thank you, Daniel. We have, I think, 16 Spark and Cassandra nodes. Basically, there's 8 and 8. So we basically have Spark and Cassandra running locally together, like per cluster. So like the process in Ninja cluster you've seen, it's 8 and 8. And those are need some help, Daniel.
They're, I think they're M3 or
Yeah, they're pretty big, right? I think there's a 30, like our master node is for, I think it has like 60 gigs of RAM, and like the worker nodes are like 30. So whatever instance those are, like M3, double X or quadruple X or whatever.
Masters and R3
Yeah, it's R3, yeah. Answer your question?
Yeah.
How do you build events from the Cassandra?
Can you repeat that question?
How do you build events from the Cassandra? You don't give them away. So you actually build the event out, you move them out to the recipe, and you give them.
So the question was, how do we move events out of Cassandra? So we actually just straight up TTL the events in Cassandra, but we're also using something called C-Core to pick up events straight off of Kafka and push them into S3. And we have a replay mechanism set up so that we can replay the events straight back from S3 back into Kafka. So if we need to replay a month, we can just kind of fire that off.
So we are using the same stuff. Can you elaborate how do you do replay and event when you actually going to do replay, it's going to be in the D2.
Right.
Or how do you tackle that?
So I actually cannot speak specifically on the replay thing. My coworker Fu, if he was here, could answer that because he wrote that piece. I think we're actually running our own little Spark cluster to do that too, just reading the files and pushing it in. To be honest, we have not addressed the issue of if I have a partial day and I want to replay the events from that day like a month later, how we would deal with that. We've handled the case of I've lost the entire day and I can replay the entire events from that day and then be okay. But a partial day would get strange because the TTL would have already expired. So our current plan is just to blow away data for the day, replay all the events for that day, and then treat them as if we were starting from scratch. The question was about the fact table. It was if we were using Cassandra counters. Yes. Sorry, can you repeat that? Sure. So the question was, what is our key in the fact table? Our primary key is actually fairly massive. It's every single dimension that we might ever care about. And that forms the partition key with the clustering key, which is also part of the primary key, being date time. We round to the hour. So it's a timestamp object. So does that kind of answer the question? Talk to me after and explain to me why it's a terrible idea. I would love to hear it so I can make it better. Sure. So so the question was, can you explain a little bit about the Spark streaming infrastructure, the batch size, the number of receivers, things like that? So we actually are using Spark 1.3.1, which is probably a terrible idea, but for right now it's working well for us. So we're using the receiverless model of Kafka streaming, so we don't have to define the number of receivers. We have just one executor per machine, and our batch window size is actually 60 seconds right now. It was much lower at the beginning, but we found that we were getting a lot of empty RDDs coming in. So if you had like 5 seconds and your system takes 7 seconds to process, you'll see a few empty RDDs come in and then one with a lot of stuff in it. By switching it to 60 seconds, we kind of paired up with our Flume delay anyway so that we get a full batch of stuff from Flume. We insert all those events and we do it again. So it's not quite real time, but it's streaming every minute, which has been fair enough for us. So the question was, what are the biggest pains we've run into, both with Spark and Spark streaming? Personally, the biggest issues I've had have been, I write tests, I have sample data that is all accurate, and then I run it on the cluster, and I get completely different errors than I was seeing in my tests that were passing. So the development cycle there has been not that great. But other than that, my main issues have basically just been Cassandra. I messed up my partition key on the fact table at the beginning and was using the date time as the partition key. And the job went from running 14.4 hours with that to the new partition key that I'm using to half an hour. So you can really screw yourself there if you're not careful with how you divide it, which is why I want to hear his advice later.
When you say hitting Spark bug?
Oh no, it's definitely bugs in my code. It's subtle bugs in my code, typically because the sample logs that I grab do not comprise the full set. Or it's just there's something different with running on a cluster that sometimes crops up in weird ways. Like I've seen my local Cassandra might be slightly different version from the one running in production, though it should be identical, where I'll be able to run a query on my local and then it complains when I run there. Yeah, most of my other issues with it have been related to the Spark Cassandra connector, which isn't really germane to Spark issues itself. The question was, do I see decent performance out of the Spark Cassandra connector? I would say I've seen surprisingly good performance. For writes, it's really fantastic. For reads, I have some concerns because I don't. The idea is that it's supposed to be able to handle a full table scan, but I'm not completely confident that that's true as the table continues to grow. If you read about their architecture thing, I think there was a talk a few times ago talking about how they make it work, and they really rely upon data locality. So you're supposed to co-locate your Cassandra nodes with your Spark nodes, and then when you run the Spark connector, they each query themselves and only pull data from themselves and somehow deduplicate that data across each other. And then in an ideal world, they would also write only to themselves, but that can get scary with nodes dying and stuff like that. Does that kind of answer the question? So, the question was, what kind of consistency are you using? So by default, it does local one read and local one writes. What we're doing is we're doing local one reads so we can pull data out, filtering locally, and then writing with a local quorum, because that's a much smaller data volume, and we have to be okay with that at some point so we don't hit ourselves and double count things. Sure. Tony, do you want to take that?
Sure.
The question was, how are you managing the Spark nodes? Are you using EMR? Are you using Yarn? Things like that.
Sure. So right now we're not using Yarn. We are looking into using that kind of the next steps for resource scheduling. As far as, I guess if you take a step back from provisioning, we don't use EMR. It's all hosted by ourselves, right? We use Chef, right? We basically set up and manage the provisions however many machines that we need. As far as monitoring, that's something that we're currently looking into right now. Like we're trying to take advantage of, we were looking at different vendors. That's been a little bit of a challenge right now for us.
It's not really elastic then. Is it elastic? Like is it able to scale up and down?
So the question is it elastic? Right now it is not elastic. Right now this is all manual.
What kind of monitoring do you have in place to make sure you're not losing data anywhere?
So the question is, what type of monitoring do we have to ensure that we're using data anywhere?
So the truth is that right now we don't have a lot of monitoring that. We have a lot of testing beforehand, and we're running separate tests to make sure that we're not losing data. The plan is that we're going to be outputting to various real-time platforms that we're going to set up alerting systems on once we kind of get a baseline, but we haven't gotten there yet.
As far as testing Spark streaming,
The question was, how are you testing Spark streaming? And you're exactly right. So what we're doing is we're mocking out RDDs that look kind of like Kafka dstream RDDs, and then sending them into a function that takes dstream RDDs, and that's exactly the same interface that it has in the main function, and we're just kind of shortcutting it within the tests. I can't remember exactly why I had so much trouble having it read directly off of Kafka, but I remember trying to set it up, kind of getting it working, but it ended up breaking all my other tests. And so I ended up having to disable it, but I was just talking today, I would really like to find a way to be able, we're using Docker for all of our testing, so we actually are running a local Kafka, a local Zookeeper, local Cassandra. So we would really like to have a whole integration test on your laptop, but we haven't quite gotten all the pieces together yet. All right. Thanks for coming. We'll be around to talk after.